In this video now, we're going to discuss the multiplication rule for probability, the basic concepts. And then in 4.5, we take the multiplication rule and dissect it further into a more formal discussion about conditional probability and independent events. Now, in 4.3, we used the addition rule when combining events with the word or. The probability of one event or another event is found by using what we call the addition rule. And that word or is synonymous with the process of addition when it comes to finding the probability of one event or another occurring. Now, when you hear the word and as it relates to combining two events, you should start thinking about multiplication. However, there are times when calculating the probability of one event and another event occurring at the same time is just a matter of identifying the frequency on a contingency table. For example, in exercise 18 on page 182 of your textbook, we are given the following contingency table, giving the frequencies now of blood antigens from a sample of 100 subjects. Now, you can have the A antigen, you can have the B antigen, or you could have both, or you could have neither. And then you could also have the rhesus antigen types. That gives you all 8 different blood types that people can have. The way that we traditionally describe them is you can have AB positive, you could have B positive, A positive, or O positive blood. Or you could have AB negative, B negative, A negative, and O negative blood. But as they relate to events, well, for example, these 35 people would represent the number of subjects that have A and, at the same time, Rh positive blood. So, when we were given this contingency table, remember one of the things we like to do is to find the marginal distributions, the row and column totals. So there are 45 people with O-type blood, 40 total people with A blood, 10 people with B blood, and 5 people with AB. Those are the sums of the 4 columns. And then we add up the rows. The number of people with positive blood is 86. The number of people with negative blood is 14. And then if we added our rows and columns correctly, it should come up to, for both the total number of group type bloods, as they call them, or positive and negative, is 100. That's also supplied down here in the bottom where they say, if 3 of the 100 total subjects are randomly selected. So, yeah. Now, from here, one of the things that's of interest is this. They say we're going to select 3 subjects at random and with replacement. The concept of with and without replacement was discussed in a previous video about the multiplication rule for counting. I encourage you to view that video if you haven't already. But they say if we're going to select 3 people at random with replacement, that means, yes, we're going to test one subject, put them back now into the population, and then potentially select them again. We want to know what's the probability that all 3 subjects are of type B and Rh negative. That's to say, we want to first identify that the probability that one person is type B and, at the same time, Rh positive. And now that magical word and normally tells us to multiply stuff, but in this case, we don't need to because we can just identify the number of people who are both type B and at the same time Rh. That's 8 out of 100 total people, which written as a decimal is 0.08. And from here on out, I'm just going to refer to this as the probability then instead of B and RH, I'm just going to refer to it as it's more commonly known as B positive blood. Now, consider this. Suppose now we're interested in calculating the probability that 3 people selected at random with replacement have B positive blood. Well, using the multiplication principle, you can think of it like this. We have 3 people that we're going to select. The probability that the first person chosen at random has B positive blood is something we've already calculated, right? So this is the first person. And we want to know what's the probability that first person has B positive blood, which we already know is 8%. Now, we test that person and we put them back into the population, and now we pull another person and test their blood. And for that second person, we're going to be interested in knowing what's the probability that that second person has B positive blood. Now, because the first person was put back into the population and we could potentially pull that person back again, the probability that the second person has B positive blood is still 8%. Because the numbers haven't changed from our population, say, of 100 subjects. Now, suppose we pull a third person, and we're going to be interested to know what's the probability that their blood is also B positive. Then, since we're drawing our subjects with replacement, then all of the relative frequencies are still the same because we put the previous 2 subjects back into the population of 100 in this case, and the likelihood of pulling a person with B positive blood still has a relative frequency of 8%. Now, given these 3 probabilities, if I were interested then in the probability of what? If we want to know what's the probability that all 3 types have B positive blood, that's to say we're interested in calculating the probability that the first person has B positive blood, and at the same time the second person has B positive blood, and that the third person has B positive blood. Well, if I'm interested in the probability that we have the first person with B positive blood, and at the same time the second person has B positive blood, and the third person has B positive blood, that all 3 people have B positive blood, then the word "and" tells you, yeah, we're going to multiply these probabilities together. That's going to be 0.08 times 0.08 times 0.08, right? And we break out our calculators, right? Or, count on our fingers and toes, 0.08 times 0.08 times 0.08 to give us a probability, and it's a small probability, 0.000512. Right? Your calculators may even give it to you as scientific notation. They may write it as something like 5.12 e negative 4, which is to say 5.12 times 10 to the negative 4th power, right? This is just your calculator's way of scientific notation. In other words, if you want to find the decimal representation, the explicit decimal notation instead of scientific notation, you move that decimal point 4 places to the left to get 0.000512. Now, that's with replacement. Suppose we're interested now without replacement, which is to say, I want to know, again, what's the probability of B positive blood and B positive blood and B positive blood, where we have B positive blood for the first person chosen, the second person chosen, and third person chosen, where now, when we inspect each subject, we don't put them back into our population, and that eliminates the possibility that we could potentially select them again, which is going to change now the relative frequencies. So now look, you see the words "and" and it's still a matter of multiplication. Right? Because when you hear the word and, if it can't just be explicitly identified from within the chart, and it involves really a sequence of steps, first person, second person, third person, it's going to be the multiplication principle. But now, first person. Well, the first person is exactly that. There are still 100 people, 8 of them have Rh positive blood, so it's going to be the probability that the first person has B positive blood. That's 0.08. 8 out of 100. Right? Now, the second person. If we're drawing 3 people at random, and now we've already selected one person, and that person has B positive blood, because we want all 3 of them to have B positive blood. If that first person has B positive blood, now we no longer have 8 people with B positive blood in our pool any longer, because we are drawing these selections without replacement. That leaves 7 people now with B positive blood. That means our overall distribution has changed. The counts have changed because we have one fewer person with Rh positive blood, and now we have 99 people left, because that one person is also not only a loss to the B positives, but a loss to the overall size of our sample space. Therefore, what we've found here for the second person is what we call a conditional probability. It's the probability that we get a B positive blood person on the second try, given that the first person was B positive. Something has occurred. That's the condition. We know that. We've already got one person with B positive blood. So what's the probability the next one, the second person, has B positive blood? Well, there are 7 remaining out of 99. Right? So that's not quite 8% anymore, right? You plug that into your calculator, 7 divided by 99, you're going to get a nice result, 0.070707, so about 0.071. But now, how about the third person? Now, at this point, the third person has been preceded by a B positive person and another B positive person. That means now, by the third person, we only have 6 B positives left out of 98. So really, this third person is also a conditional probability. It's the probability of getting a B positive person for the third person selected, given that the first person was B positive and the second person was B positive. Right? Because these conditional probabilities restrict the size of your sample space. And you can see in this case, yeah, because the first person and second person who were drawn without replacement have B positive blood, that changes not only the number of people with B positive blood, but also the size of your sample. The size of your sample has been restricted to 98. So the probability the third person has B positive blood is 6 over 98. Plug that into your calculator, right? You also get a nice little probability, 0.061. So the probability that someone has B positive blood as the first, B positive blood on the second, and B positive blood on the third. The ands tell you multiplication, but now look at the probabilities. It's going to be the product of 8% for the first. We calculate it as 0.071 for the second and 0.061 for the third. So the probability that all 3 people have B positive blood is going to be 8% times 7.1% or 0.07 times 6.1% or 0.061, which gives us a probability of 0.000346, which if you wanted to write that as a probability, move the decimal point 2 places to the right now to 0.0346%. So the probability of getting 3 people with B positive blood from our pool of 100, in this case, this would be our population of 100, then would be very, very unlikely. And that's the multiplication principle.